chopped and, that's better. Very good.
Is better now?
Yes,
okay.
Yes, better. Thank you very much.
Thank you. Yeah.
Okay, so thank you for giving us the chance to listen to your lecture because it is very interesting. Many of our, not only students, of course, our professors, even you have chat with our rector just now. We are keen to hear about your experience, about your knowledge, especially, of course, the motivation behind everything. Because I've read your biography, a short biography, and I think it's quite very interesting in the way that you are consistently focusing on this area. So many people have influenced you, and of course, I think you have influenced a lot of people. So I would like to probably first, of course, you have met our rector, but I would like officially to introduce you to our rector, Professor Ari Kunchoro. He is now also in the Zoom meeting, and also many of our head of university, vice rectors, academic affairs, Professor Abdul Haris, vice rector of finance and logistics, Mrs. Vita Silvira, secretary of the university, Dr. Agustin Kusmayati, and also vice rector of human resource and assets, Professor Dedi Priyadi, DA, which also graduates from France, by the way. So there are also lots of guests now attending the Zoom sessions. We have many researchers, academicians also from not only Universitas Indonesia, but also from many other, let's say, research institutions, partner universities surrounding all around Indonesia. So we are all keen to hear from you. And also our students, there are about 8,000 students now watching you from YouTube. These are new students and also others which are also our old students, or let's say more senior students who are also, some of them are attending also in this Zoom meeting. So there are lots of people that are going keen to hear from you. And probably at first I would like to introduce Prof. Ari Kunchoro, if you want to have some welcoming or let's say hello to Professor MOUROU, please, you may do so.
Hi, Professor MOUROU. Welcome to University of Indonesia. It is a little bit unfortunate that we cannot have on-site event, but I think we have to accept that this is modern era. Yes, it is the time for us to use technology. So again, I'd like to thank Professor MOUROU for delivering a general lecture to our student. It is my honor as a rector and also our honor as the University of Indonesia. So again, welcome to Professor Gerard MOUROU. I think we have been listening to your lecture. Thank you very much.
Thank you. Thank you very much. And I would like also to really also to thank you very much, Professor Ari Kunchoro, for these invitations. In spite of the fact that, you know, it's in the middle of my holiday vacancies, you know, I'm vacationing in the south of France, but that it's a pleasure to be with you and to deliver this lecture on one thing which is very, very dear to me. It's about light and extreme light. Okay.
Okay. Thank you, Professor Ari Kunchoro. Thank you, Professor MOUROU. Maybe we will start immediately with the lecture. And before that, I would like to present and also read a little bit about Professor MOUROU, so that we know, or everybody might know about him, but probably I would just have to, of course, introduce officially. Allow me to introduce you, Professor MOUROU. So, Professor Gerard MOUROU is professor, member of Haute College of École Polytechnique, A.D. Moore, Professor Emeritus at the University of Michigan, Ann Arbor, Michigan, and the director of the new center, IZEST, or International Center for Zeptosecond Exawatt Science and Technology at École Polytechnique. Mr. Gerard MOUROU was born in Albertville, France. He studied physics at the University of Grenoble, and then at the University Pierre et Marie Curie in Paris, where he earned his PhD in 1973. He later moved to the United States and became professor at the University of Rochester, where he did his Nobel Prize awarded work along with Donna Strickland. He subsequently worked at the University of Michigan and then École Polytechnique in Paris. He is recognized worldwide for his work in ultra-fast science and technology, mainly for his co-invention with his student Donna Strickland of the laser amplification technique called Chirped Pulse Amplification, or CPA. In 1985, Strickland and MOUROU succeeded in creating ultra-short, high-intensity laser pulses without destroying the amplifying material. First, they stretched the laser pulses in time to reduce their peak power, and then amplify them, and then finally compress them. The intensity of the pulse then increases dramatically. Chirped pulse amplification has many uses, including femto-ophthalmology for corrected eye surgery, especially for cornea and cataracts. The CPA has been the gateway to attosecond field and high field physics. As such, he is often revered as the father of ultra-high field science. He returned to France in 2005, proposed the creation of the European infrastructure, ELI, or Extreme Light Infrastructure, and he was the coordinator of its preparatory phases. It is a 1 billion euro facility, ELI. It's built on 3 countries, the Czech Republic, Romania, and Hungary. It's dedicated to the production of extremely intense pulses as a novel paradigm to high-energy particle physics. Gerard MOUROU is a member of National Academy of Engineering, USA. He is also a foreign member of the Russia Academy of Sciences, Austria, and Lombardy. So please welcome Professor MOUROU for the lecture. The time is yours, Professor.
Okay, I have to share my screen, I guess, now. I'm sorry, I'm trying to share my screen with you.
Yes.
I don't understand what's going on.
Or we could share it for you.
Yeah, okay,
Yeah?
it's fine. Yeah, good.
Good. So,
If you
okay.
can.
Yes, we can. So you can just say continue or... So now it's shown, Professor.
Is that, it's okay for you now?
It's okay?
Okay.
Yes.
So do you see, is it, I mean, you see the full screen where you are? Hello?
Can we?
Can you hear me?
Yes, yes.
Okay, so I can go.
Yes, you can
Right?
go.
Okay, so thank you very much for these invitations, you know, and to be, I'm very glad this way to be acquainted in a sort to this really nice university and prestigious university of University of Indonesia, okay? Thank you very much. You changed my screen, and this is good. Okay, so as I say, really very, very pleased to be here, in spite of the fact that, you know, I'm right now vacationing in the south part of France, in what we call Provence. So let me tell you my passion for extreme light, okay? And I'm really pleased to also introduce my graduate student, Donna Strickland, who shared the prize with me, okay? And when the Nobel committee called me, you know, on the Tuesday, the first, you know, that the Nobel Prize for Physics is always on the Tuesday, the first Tuesday of October, okay? And so when I got the call, of course, I was really extremely pleased, not only for me to get the Nobel Prize, but also I was doubly pleased because of Donna Strickland, my student, you know, got the prize. And I have to say one thing about that, because Donna is a third woman, you know, behind Marie Curie and Maya Gopper-Mayer to get the prize, okay? So it was an extreme honor for me, you know, her advisor to have also advised a Nobel Prize winner. That was very, very nice. Okay, so I'm going to talk to you about light, okay? Can you switch light, please? Can you switch it? Yes. I'm going to talk, no, come back. Yeah, thank you. So I'm going to talk about light, and of course this is, I'm starting, you know, from the very beginning with just a light bulb, okay? And the light bulb, in fact, generates incoherent light. And, you know, I mean, all the photons which are really emitted by this bulb, light bulb, you know, are incoherent. You know, they have no relationship between each other, and they go in all kinds of directions. Now, next slide. Now, this is a laser, okay, of course, and you see the laser is what we call a coherent light, and I will say a few words about this, but you see that now the light is going mainly in one direction, and plus is made of kind of unique kind of photons, okay, not as, and they are going all in the same directions. So next slide. So the light from a laser can be emitted, can be continuous, or I will show you, also can be also emitted in bursts of light, sometimes very short bursts of light. Next slide. Yeah, the bursts can be extremely short, and this is the one I'm going to talk about mainly. They go in, they are measured in a femtosecond. Femtosecond is a billionth of a millionth of a second, okay? It's 10 minus 15 seconds, billionth of a millionth of a second, okay? So this is extremely short, and you will understand why sometime we need to do that. Next slide. Yeah, so now I'm coming back to the light, okay? I talked about incoherent light, okay? And incoherent light is very much like a bunch of marathon runners, you know? And you see, marathon runners, they go in one direction, roughly, okay? But they they are all dressed differently. They don't know each other. They have no relationship with each other. And they, of course, go at different speed, different pace, okay? Next slide. On the other hand, a coherent light is very much like an army marching, okay? Where now all the soldiers, are wearing the same uniform strictly. They go strictly at the same pace, okay? And if you know the position of one soldier, you will know the position of everyone, okay? And this is very much like a coherent light, okay? So next slide. So this is Ted Mayman, okay? He is really the inventor. Inventor is really Charles Townes, but Ted Mayman was the first one really to make a laser work, okay? In 1960, in fact, it was it was May 1960, okay? Then Mayman made the first light with his laser, and you see the laser in his hands. At that time, it was very rudimentary, okay? And so now, what is amazing about these lasers? If you take one laser, okay, you can almost, you can do so many things, okay? And you will understand why. Okay, next slide. So if, for instance, if you're taking a laser, I can have this laser slow down atoms to almost rest, okay? And so that means, next slide. So that means that when you are slowing down atoms, we physicists, we say we are cooling atoms, okay? Because the temperature is, of course, an expression of the motion of the atoms. So we can really slow down atoms, that is, we can cool now atoms to very, very low temperature, and there is a huge amount of really applications now where you really need extremely controlled cold atoms, okay? In metrology, in this number of applications. So this is the thing. One thing you can do with laser, you can slow down atoms, cool atoms. But what you can do also, you can almost do the opposite, okay? Next slide. Yeah, you can accelerate particles to almost the speed of light, okay? This is very important. So you see, you can really do this two very different things. So you can accelerate particles. So next slide. So the particle gets energy in a giga, very high energy range, like many giga electron volt, and soon I hope we will get the TeV, tera electron volt. So you see that with the same photons from a lasers, you can basically produce events with almost 30 or 25 orders of magnitude, okay, in terms of energy. So this can explain, you know, why we can really do so many things with lasers, okay? By the way, here with the high intensity laser, with very short pulse lasers, we are in a situation where we are going to accelerate particles, right? And we are going to produce accelerate particles to the relativistic regimes, okay? The particle will go at very close to the speed of light. And so the applications will be in accelerator physics, in nuclear physics, cosmology, nonlinear QED, general relativity, and you name it, large number of applications. And of course, this is what I'm going to talk about, okay? Mostly about high energy that are produced by the lasers, okay? And this is the reason why I got the Nobel Prize. We got the Nobel Prize with Donna. Next slide. Okay, now, why do we want to have very, very short pulses? Well, we can, if we want really to get very high power, then, you know, if you have a very short pulse, it's very easy to get very high power, okay? Let's take, for example, 1 joule. And if you produce 1 joule burst of light in 1 femtosecond, you know, the peak intense, the peak power is in a femtosecond regime. And a femtosecond basically is the power of all the electrical network in the world, okay? So, but of course, this, you do that for only a femtosecond, okay? But then nevertheless, that really gives you a sense of what we can produce with extremely short pulses and why sometimes you would actually to get very, very short pulses instead of a steady long pulse. Next slide. So now you see, for instance, if you take this very high peak power that you have produced, as I say, 1 joule, 1 femtosecond, petawatt, and you focus this beam over a very small spot size, limited by the wavelength of light, of course, limited by the diffraction of light, then you are producing phenomenal pressures, okay? Pressure equivalent to something like 10 million Eiffel Tower on the tip of your fingers, you know. So this is very extreme pressure, of course, and it is the highest pressure that we can produce now, okay? So you can see already what we are going to do with this type of light, because we can really produce these extreme conditions. Next slide. So this is, I will say, not exactly a typical, but I mean, one of the lasers which is producing the highest power in the world. It's about petawatt lasers, you know. They are relatively compact, okay? Of course, you don't have to have petawatt laser, you have also terawatt lasers, you know, and so on. So, and, but this one is one of the petawatt laser, one of the most powerful lasers, and which are going to give us, you know, this incredible power. Now, next slide. Okay, next slide again. Next slide. Next slide, please. Yeah. Okay, now I'm going to talk about how can I get this extreme power, okay? We as I said, we start with a short pulse of light, okay? And a pulse of light comes out from what we call an oscillator, okay? And if we are taking this short pulse of light, with this at the beginning, and if we try to amplify the pulse with what we call an amplifying medium, there's a number of amplifying mediums that we can use, but if you try to amplify, trying to get more out of your pulse, then with a short pulse, what you are going to do, you are going to damage the amplifier. You are going to reach a ceiling very quickly because the pulse is short. So if you amplify it with relatively small amount of energy, you will reach, a very, very high intensity, and you will break down the material. Okay, and that is the problem. Okay, that was we were stopped by these problems for a long time. Okay, and then we came with the idea with Donna Strickland that before we were not going to amplify the short pulse directly, but before we will stretch the pulse. We will stretch the pulse. So when we started, we stretched the pulse by a factor 10, and then by a factor 100, after 1,000. Now we stretch the pulse by a factor millions. Okay. So what we do, we are reducing, of course, the intensity of the pulse accordingly. And then you can now amplify the long pulse. Okay. And we are using these grading systems, these diffraction grading systems, to really stretch the pulse. And we can do it so we can have, say, the red part of the pulse, going first, and the blue part of the pulse going last. And we can control that with the diffraction gradings. So when the pulse is stretched, then we can amplify it. And when it's being amplified, then we are going to do just the converse of what we have done. Okay, that means we are going to compress back the pulse, to this initial value. But this time, we are going to have a pulse with much, much more energy. Okay, 1 million times. Okay, more. And that was a trick. And of course, you have to do that very, very well, very carefully, because if you take femtosecond pulses, you stretch something like 1 million times, means you stretch it back to a nanosecond, okay? And then you are compressing it, amplified by 12 order of magnitude. And then you are going to compress it, 9 order of magnitude. So you have to do that very, very well if you want to have a very clean output pulse. Okay, next slide. And now with extreme light, you will see that we can produce, as I said, the largest peak power, the largest temperature in billions of degrees, okay? Much, much hotter than the sun, okay, at the center of the sun. You can, as I said, you can produce the largest pressures. We can produce the largest acceleration. We'll be able to accelerate particles from 0 to the speed of light in a femtosecond, which means that you are producing phenomenal accelerations in 10 to the 25 G. Phenomenal, okay? So you see that you can do many, many, many things. And that's the reason why this field is so important now. Okay, next slide. Next slide again. Next slide, yeah. So now, you see, could you come back to the previous slide? Yes. Now, what I'm showing you is just atomic systems, okay? Where you have a nucleus, which is really composed of nucleons, protons, neutrons, and you have the electrons, you know, circling around this nucleus, okay? So until now, with the laser, you know, we were only, and with optics in general, what we do is only to to excite the electrons, okay? This is what we do when you shine a light, you know, on a wall, you are going to excite the electrons circling around a nucleus, okay, these kind of things. And because they circle around, they are going to re-emit the light that you get, and you are going to see the wall. Now you will see, and now with the laser, with a high intensity laser, then we are going to see that we can change things. Normally, you know, the electrons here, even with just common lasers, the electrons are not going to move by a large range, by big excursions. You know, it's a really relatively small amount of displacement. But with the laser, high intensity laser, now these electrons are going to move at the speed of light around the nucleus. And so they will move, you know, over very large excursions. Typically, the wavelength of light, okay, huge amount. And that's the reason why, next slide. Yeah, so now with the high intensity lasers, you see, we are going to move from the atomic, I will say, physics, where the laser was before the CPA, to now the subatomic regime, okay? So from the electron volt regime, this is the domain of optics, to the subatomic regime, which is giga electron volt or something, and so on. So we will now, instead of studying only the atomic systems, we are going now to start to study the nucleus systems, okay? And because we can produce this phenomenal displacement. So let me, next slide. Yeah, I'm going to now describe a few applications, okay? And this here, this is the history of over many, many years, you know, starting in 1960. I'm sorry, this was, you cannot see it. It's starting with, start with Ted Mayman, 1960, you see, and where the intensity of the laser he produced with his ruby laser was about 10 to the 8 watt per square centimeters. It was a lot at that time, but now, of course, it's nothing. And so the intensity increased, starting 10 to the 8 watts per square centimeter, gradually increase by using different techniques, and came up to about a ceiling which was about 10 to the 14 watt or so per square centimeters. And here you have this big plateau and we stayed about for 20 years on this plateau, and it was a 10 to the 14 watt per square centimeters. It was basically, this plateau was due to the breakdown, energy of most materials, at 10 to the 14, 10 to the 15, you are breaking down the materials, you are separating, the electron from the nucleus, and you are breaking down the material. So then that stopped at 10 to the 14 watt per square centimeters. So in 1985, this is where we came with Donna, with a Chirped Pulse Amplification. Then we could circumvent these problems, and now we could really continue to climb up this curve. And so by increasing the power, we will really now going into different regimes, physical regimes. So I'm going to talk a little bit about these regimes. I would like just to, the one in purple here is a regime where we ionize materials. And one of the applications, for instance, I'm going to show, there's many applications, but one the most right now used is the micro machining, okay? Micro machining, you will see that we can really machine with exquisite precisions with femtosecond pulses. Now, if we increase, if we are increasing this intensity now to tend to be 18 or so watt per square centimeters, then what will happen is the quiver energy of the electrons, which oscillate around the nucleus, will reach velocity of light. Okay, and that was the first time. The electrons, normal electrons, submitted to normal light, the electrons are very, very low velocity compared to the speed of light. Okay, but now we will be able really to reach electron will reach speed of light velocity. Okay, and that, of course. And so what happened is the mass of the electrons, of course, is going to change, okay? And so everything will change in optics, okay? Now, optics in these regimes, is completely different. And we call it relativistic optics now, okay? Because the electrons now around the nucleus will become relativistic. Now you have, if you go up in a yellow band, then not only the electrons, but the much more massive protons, will be able to be accelerated, okay, and to the speed of light. So we will be able to make relatively easily, relativistic protons, for instance. And when you go even higher, 10 to the 20, above 25 to 10 to 29, in fact, what you are going to get is you will be, the field of the laser is so large, okay, that you will break down the vacuum, okay? You will break down vacuum in its components, electrons, positrons. So you are going to generate, you start with light and you will produce matter. So you will materialize light, okay? Which of course is something, it's one of our dreams, to do. Is we are not quite there yet, but yet, I'm sorry. but we are very close, okay? So, so that gives you a little bit some idea, but of course there's really many other applications, but just give you an idea of what you can do with light now. You know, you can create matter with light, okay? Okay, next slide. Next slide. Next, yeah. Okay, I'm starting now with the micro machining, okay? As I said, the one at the bottom. So if you have pulses not so short, say beyond, 10 minus 9, a nanosecond pulse, 10 minus 9 seconds, you know, which is very long for us, okay, because we are working in a femtosecond, a million times faster. Well, if you are using nanosecond pulses to do some machining, you know, you can do it, of course, and people are really doing it, okay? But what happened is the fact that when you send the pulse on your target, you know, in order really to machine the material, then the pulse is long, is a little bit long, so the temperature is going to really to be to diffuse, you know, around, spread around the spot size, and so you are going to elevate the temperature a lot around the spot size. So you are going to basically make a big crater, okay? A crater much larger than the spot size itself, okay? Now, if you are using, because the pulse is long, because the pulse, for a nanosecond, the temperature has a time to propagate, the heat has time to propagate. Now, if you have a short pulse in a femtosecond time scale, so a pulse which is a million times faster, then what happens is, of course, you are going to hit your target, but this, you are going to raise the temperature of the area you're hitting with the laser, but nothing, you are going, the temperature doesn't have the time to spread out, okay? So you will remove just a relatively small amount of of material. So you will be able really to do an extremely clean job, very accurate. Okay, let me show you. Next slide. Yeah, for instance, if you are using, you see, femtosecond pulses, you can really do all this exquisite, you see all these holes that you can really punch, you know, and look, they are all the same. They're all the same. And the diameters is 1/3 of a micrometer. You see, look at how sharp are these holes. Very, very sharp, okay? So this is really really the best way to do machining, really, okay? Now, next slide. And now what, of course, if you want really to do exquisite machining, of course, as an application, you think about ophthalmology. Because in ophthalmology, what you like really to do, of course, is to do very, very, what you need to have is really a very accurate scalpel, right? And so you can cut things very, very cleanly, okay? And let me show you, next slide. Yeah, for instance, if you want, you know, this I show, for instance, a retina, okay? And the retina, you know, is about 500 micrometers in thickness. So what you can do, you can really send the lasers, focus it in within the retina, and make, so each pulse is going to make a bubble, okay? A very teeny tiny bubble. And if you move the laser around, you can in fact cut, the material in what we call flap. You can make flap, very, very exquisite flap. Okay, next slide. Yeah, for instance, that is the kind of flap you can really produce on a cornea, or here, of course, on the cornea of the pig. But now, we have this procedure has been done, and it's a very huge success because more than 2 million patients a year have this procedure now, just to correct for the visions, or for if you have cataract, if you have problems with the cornea and so on, of cataract and so on. You have 24 million eyes a year now. No, it's 2 million eyes a year, and 24 million since we came up with the applications. Yeah. Okay, so these are gorgeous applications. Okay. Next slide. Yeah, and also you can do things like corneal transplant, and so you can do that because you have, instead to have like a mechanical trifine where you really are punching, you're using a razor blade, basically, you are using now the laser, and you can have much larger flexibility. Okay, next slide. Okay, now I think I'm going to the green area. The green area, I told you, is where the electrons can be relativistic. Okay, they are accelerated by the laser. The field of the laser is so large, then the electrons now are moving, at the speed of light. And that's the reason, again, we call that relativistic optics. Okay, and now next slide. And what we are going to do now, we are going to try to accelerate particles, okay? And you will see that we can accelerate particles in a very compact manner to very, very high velocity. I mean, the speed of light, of course, but I mean, with a very large Lorentz factor. So, and what I'm going to describe here is a technique which is being used, which was proposed by Tajima and Dawson in 1979, where now what we are going to do is next slide, I'm going to show you. Sorry. Next slide. Yes, thank you. What I'm going to do now, I'm talking about electron accelerations. I'm going to use a focus a laser in this gas jet, noble gas jet, okay? And, like a millimeter in size. And what we are going to do, we are going to focus the laser in this gas jet. Doing that, we are going to really produce a plasma of electrons and protons, basically. This kind of a soup of electrons and protons. And you are going to produce a plasma, and the electrons are going to drop into the trough of the plasma wave here, and are going to be accelerated because they are trapped. And the plasma wave is produced by this laser, this very short pulse, right? Because remember that the pulse is in femtoseconds, okay? So the size, I mean, the size of the pulse is in micrometers, okay? Just speed of light, okay? A femtosecond at the speed of light, you get micrometers, okay? So you have this this wave of space in micrometer scale, and they will be dragged at the speed of light. And what is phenomenal is we have shown that now we can accelerate particles to energy of giga electron volt. Giga electron volt per centimeter. Now you say, okay, you maybe don't understand this, but giga electron volt per centimeter is enormous. If you consider that with a conventional technology, next slide, yes. If you want, I'm sorry, I don't understand that. Yeah, if you want really to accelerate particles now with conventional technology, it will take you, a giga electron volt will take you, people like this, 300 of more, like accelerator of 300 meter diameters. So huge compared to single centimeters, okay? So that you understand. Next slide. Yeah, one thing also, I'm talking about accelerator because accelerators is very important for the society, okay? Not only for science, but for society is very important because you can produce many things, okay? And I will show you that some of the applications, particularly in medicines, nuclear medicines and so on. So next slide. Next slide. Yeah. So now I'm going to talk about some of the applications. So I'm going to talk about low-hanging fruit. The fact that we can accelerate particles to very high energy. I'm going to show you now some of the applications, in the medical field, but also in the environment. For instance, one of the applications right now will be maybe to get rid of the nuclear waste, okay, and so on. So next slide. Next slide. Yeah, we go to next slide. Next slide. Please, next slide. Yeah, thank you. So now we can just going a little bit fast here, but we can accelerate electrons. We can also accelerate protons, okay, and to very high energy. I showed you that if you want to do that, if you, for example, want to accelerate protons with close to GeV energy, it will take you humongously big machines like this one, which is almost a kilometer, to accelerate protons to the speed of light. Okay, and of course, this is a very costly machine, and we can do that with the laser over millimeters. Okay. Next slide. Yeah. Some of the applications, for instance, why do you want really to produce protons, accelerate protons, for instance, to fraction of GeV, so speed of light, close to the speed of light? Because you have fabulous applications. And one application is, for instance, proton therapy. Okay, proton therapy is much better than X-ray therapy or electron therapy. Okay, if you have a tumor, for instance, The problem with X-ray therapy and electron therapy is if you are going to burn the tissues which are before the tumors. So when you want when you focus your beam, your X-ray beam or electron beam to burn the tumor, you are also going to affect the healthy tissue in front. Well, but with protons, it's not the case. With protons, you can, if you have accelerated protons, you can select where the proton will stop. Okay, so in fact, without affecting too much the tissues which is ahead. Of course, this is an incredibly important application because because of course, if you can treat patients this way, and we know it works, okay, it works already with conventional accelerators. So what we would like to do now is really to do the same thing with much more compact accelerators and cheaper accelerators than we can really put in hospitals, you know, and so on. The other things also we can do with the fact that we can accelerate particles, you know, to very high energy, we can really produce radionuclides. Radionuclides that we can use also, you know, we can implant this nuclide, you know, into tumors and so on. And you can use also this radioisotope that you can produce for nuclear diagnostics. Okay, next slide, please. Yeah, and now I'm going to the applications about environments, especially about trying to use extreme light for producing clean energy, clean nuclear energy. This is important. Next slide. So you know that we were basically, when we are producing with nuclear power, okay, let's say we are using uranium, you know, as materials. And when you are producing nuclear power, you do that with neutrons. You are using neutrons to produce this avalanche. And no, your neutrons, of course, you are using the neutrons, you know, to fission the nucleus of uraniums and so on. Okay, and then so sometimes you fission the nucleus, and you are releasing these fissions. You know, release a lot of energy. Okay, but also sometimes. So, and you split the nucleus, okay, release the energy, but sometimes some of the neutrons are captured by the nucleus without fissioning, okay, and that leads to what we call minor actinide. And these are the species, these are really the troublemakers. Okay, so and which have a lifetimes, maybe sometimes of million years, you know, and so on. So what you likely to do now is to take this minor actinide like a neptuniums, and you are going to use the neutrons that you can produce with lasers. And you are going to fission it now, and in smaller elements. The smaller element will have a lifetimes much, you know, sometimes say 11 minutes or things like that, extremely short. Okay, so that's the type of things that we can do with lasers, because we can produce in a very compact manner, you can produce protons. And with the protons, you can produce neutrons, and with neutrons, you can really use it for what we call, that's called transmutations of nuclear waste. Okay. So of course, this is that could be a very, very important applications, and something which is really something which is very high in my priority list. Okay. Okay. Now next slide. Now, okay, we are also, and that will be my last applications of extreme light. We know that we have also this problem, and mentioned the problem of nuclear waste, but also we have problems with space now, because since the beginning of the space era in 1957, every time we launch something in space, we are also producing debris. And these debris, now you have a lot of them. You have thousands of very large debris like, I like to say, like a washing machine, okay? You have thousands of them, okay? But you have millions of them, which are very small size, which are the size of smaller than centimeters. But this debris, travels at a velocity of 15 kilometers per second, 10 times faster than the fastest bullet. So, of course, you can really do a lot. They can do a lot of damage, even the small debris. Okay, and so we have now to think about how we can clean the space. Okay, it's a good thing to really of course, space is very, very important for our society, but we have to make it sure that the space stays clean. Okay, because if it's not clean, it's going to be dangerous for the equipment that we are sending, satellites and so on, but also for humans. Okay, and if we are not capable to send, especially because now we are sending more and more and more satellite, and every time when you send satellite, you are also sending junk. Okay, so it's very, very important that we clean the space, so we have no problem, because otherwise sooner or later we won't be able to get out of our planet system. Okay, now next slide. Yeah, so just to give you an idea, we sent already the equivalent of 4 Eiffel Tower in space. Okay, we have 28,000 tons. We sent 28,000 tons of material in space, and about one half of Eiffel Tower is now circling around the globe, under the form of debris. Please, new slide. Slide, yeah. Slide again. Yes, and I'm going to show you how we can really try to clean the space. Next slide. Yes, so with the high-intensity lasers, what we propose is really to use a high-intensity laser when we can see one debris, say, like we have a ball here. When we see the debris, we try to shoot at the debris, but we don't want to vaporize the debris, okay? Because we can make more debris, okay? And also because it will be too energy consuming, okay? So what we want to do is simply really to give a nudge to the debris. So if we shine the laser on, say, on this kind of debris, what we are going to do, we are going to create a plasma, which will have a rocket effect, okay? A rocket, and the rocket effect is going to change the trajectory of the debris, okay? And the debris will fall sooner or later, you know, into the atmosphere. It will be burned into the atmosphere. Okay, next slide. And so now I'd like to conclude by saying, you know, what was very, very important for Nobel, Alfred Nobel, was really to make his, he wanted to give his prize for invention, which brought the greatest benefit to humankind, okay? And so what I think I described it to you was the extreme light and its applications. And you can see that the application is absolutely numerous application, huge amount, and a lot of them could really benefit humankind. Okay, next slide. Now, what I'd like to do, and I would like also to say one thing, is I think with extreme light, we will, the best is yet to come. We don't see the end of it. And now I'd like to go to show you a few things. It's about the Nobel Prize. Next slide. So yeah, so you receive the Nobel Prize December the 10th, you know, exactly of each year, December the 10th, you have the Nobel Prize ceremony, okay, because Nobel was the death anniversary of Nobel was December the 10th. So, and of course, this was a really very prestigious event. Next slide. So, you know, we have this phenomenal ceremony, banquet, and so on. And here, for instance, I'm sitting next to the Queen, okay? Donna Strickland was, because she's a woman, and so on, was sitting next to the King, and so on. And we had this fabulous receptions, you know. And next slide. Yes, I was also next to the Princess Sophia. So I was, the Queen was on the left and Princess Sophia was on the right. But so that was a lot of glamour and so on. But I have to say that the most, I will say, emotional moment is the next slide. Can I have the next slide? Yes, it is this one. You know, when the last thing that we do when we get a Nobel Prize, okay, of course, you have to go to the Nobel foundations, you know, to file few forms and so on, to fill a few forms and so on. But the most emotional things was at one time, and that's the last thing, okay? They ask you to go into this office, you know, and they bring you these notebooks, this notebook, you know. Nothing really, you know, doesn't look really special, doesn't look special. But in fact, they are very, very special because they have the signature of all the Nobel Prize. And they ask you to sign the book. that was very, very emotional. And I want to say that I was with my wife for 54 years. And we were together, for this moment. Okay, well, I'm going to stop here. Thank you very much.
Thank you very much, Prof. MOUROU. I think we can give applause virtually, of course. If anyone want to, you can clap from your homes. But of course, I was actually impressed with the last slide. I can catch that emotion that you express within that room, where you look at. I think before you sign it, you see all the signatures, isn't it?
Absolutely.
Yeah.
Yes, absolutely. And that really make you really humble.
Yeah. Very impressive.
Yeah.
It's like the whole. Well, these are all the history of people who made impact to the civilization, to the community, to the world.
Yeah. It's 15 minutes. When you have about 15 minutes to glance at the book, you know, because there's so much to see. I mean, you, of course, as you said, you see all the steps.
Correct.
That has been made by the civilizations.
Yes. Very impressive. Very. Of course, I think you should be very proud of yourself. To be proud of the humanity, how it achieved the progress of the civilization in the world, and how people are contributing to the best of mankind. I think that is very, of course, very touching, very impressive. So thank you, Professor MOUROU. We have a couple of questions here, Professor.
Yes.
From our students. I'd like to get into our students before we go to the audience at the Zoom meeting. There is one student asking for Christo Yeswa, his name, and he asked, Professor, did you also do a research on quantum physics? And if you did, could you give a short explanation on that matter? So I think it is from a physics student, I presume. He has passion in quantum physics.
In fact, not really. I mean, yes and no, okay? We do, of course, quantum, it's like when we speak, right? I mean, we do prose every time when we speak. In physics, we do quantums like this also. We do quantums, at very high, for the high energy, effect, okay? Not quantum like it's being done normally with, as I said, with CW laser when we are cooling things very quietly and so on, and so but of course every time when you are really producing new kind of particles and so on, of course, the quantum physics intervene. Yeah, it's at a different degree of energy. Okay, it's not at pico electron volt, but it's more like at mega giga electron volt and so on. Yeah.
Okay. So next question, Prof. MOUROU, is from Ganedra Wirata, and he has some comment, I think, also. Listening to your explanation about extreme light, I couldn't stop myself from worrying about the possibility of someone weaponizing your work. What if that happens? I think that is also one of the part where Nobel have that issue before. So this is also the common question also, I think.
Yeah. On this, because, of course, I'm asked this question, all the time. And because with this phenomenal power, you cannot resist to ask this question. But it turns out that this power is very, very special. You know, if you want really to arm something, usually you need to have a lot of energy. Let's suppose that you want to shoot down something, you know, you want to, you know, it takes energy, okay? But in our case, what we do is we are producing a lot, extreme power, but with a small amount of energy. Okay, you have to realize this. You know, as I said, you know, you have 1 joule. What is 1 joule? 1 joule is nothing, right? It takes, for breakfast this morning, you had millions of joules for breakfast, okay? So you take 1 joule, but the 1 joule, if you deliver this 1 joule of energy in 1 femtosecond, you know, you are going to produce petawatt. But this petawatt is not going to destroy things. It will be, of course, very important for if you take this petawatt and you focus it very on, you know, on a very small size and so on. So you will do things at the atomic level, but you are not going to destroy anything. Okay. You don't have, you know, you don't have the energy to destroy.
Yeah. So the essence is the size matters in this case.
Yeah, yeah. For example, you are going to accelerate particles, you know, to phenomenal, I mean, to the speed of light, you know, in a femtosecond, which means you are going to have accelerations at the 10 to the 25 G, okay, acceleration, incredible, but you know, it's going to be only on few particles.
Yeah. So now the third question from the student before I go to the audience in the Zoom meeting. It's from William Hilmy. Good afternoon, sir. What a nice masterclass. I'm William from Faculty of Mathematics and Natural Science. Okay, I'd like to ask, what do you think about the future of laser and electrical engineering? Okay.
Oh, laser, yeah, laser and electrical engineering are closely matched. Okay? In fact, when you are talking about electrical engineering, I think a lot about my dad, because my dad was an electrical engineer. And it's because, you know, he taught me a lot, you know, when I was young, you know, we were always talking about speed of light. I was very impressed by the speed of light when I was young and things like this. And, you know, it was very helpful. So he was an electrical engineer. And so I have a lot of respect for electrical engineering. But also, you have many applications. So one really, for me, is the most, I want really to, as I said, to really to finish my life, you know, trying to use short pulse laser, high intensity laser, you know, for nuclear power, okay? Like I showed, for instance, to trying to clean the debris, okay? But because as I showed, we could use the particle that we can produce, okay? The protons, and then we are making neutrons, and we can use neutrons to transmute nuclear waste. This is an application. Very, of course, very important applications. Now you can also do fission yourself. I mean, you can do fission with the lasers. There is, you know, proton bore. If you have protons produced by the laser, you can already do proton bore. You can produce energy this way And so you can really, and this is what really matters to me. Because as a scientist, I think now every scientist, we should think about how we can save the planet, okay? Regardless what you do, okay? We know that things are not going all fine, right? We have this climate change, enormous climate change, and so we have to really use our skills, our knowledge, you know, really to help to clean up the power. And I think in my case, in our case, people working in extreme light, is nuclear energy. There is many ways where you could really think we could produce nuclear energy, but in an abundant and safe way. Okay. One will be, instead of using uranium, we could use thorium, for instance, and so on. There's many ways we could really use the laser, ultra high intensity lasers, to produce clean energy.
Okay. So next, I would pick one question from the audience in the Zoom meeting, and here is from I think T.S. Chan, and he asked Prof. MOUROU, what limits the repetition rate of ultra-intense laser facilities around the world?
Very, very good questions. Very, very good questions. Of course, you know, we can, thank you for the questions. Okay. Of course, this is one of the not necessarily a problem, it's maybe also a solution, is we can produce this phenomenal peak power, you know, but the problem is we are always limited by the repetition rate, okay? So you are in a situation where you can reproduce very high peak power, but low average power, because you can repeat this pulse, you know, only few times. So now, when we started that, it was few times a second. That is, we could already go at the Hertz repetition rate. But now we can really have kilohertz systems, even megahertz systems. Okay. So what we will do now is trying to go to shorten the power. Okay, shorten the pulse durations. Okay, we are in a femtosecond regime. Okay, so we are moving now into the attosecond regime, and I hope that after the attosecond regime, we'll go to the zettosecond regime. Okay. Every time when you really move from femtosecond to attosecond and so on, you gain in peak power with the same energy. Okay. So it's a way really to produce very high intensities with relatively low rep rate, which means with relatively low average power. Mm-hmm. So right now, in my case, in my group, I mean, we work a lot, you know, to produce very short pulses in the attosecond regime and attosecond, zeptosecond regime. And what is nice also when you do that, you don't stay in the visible, but you move into the X-ray regime, mm-hmm. which is also a very good thing.
Thank you. Okay, now I'll come back to the student again. I think there are a lot of, especially physics students here, are inspired by you, Professor MOUROU. Another physics students, Department of Physics, the name is Saron Adrilia Chandra. He wrote, "Hello, Professor. I'm Sharon
Hello.
from Department of Physics. Thanks very much for the amazing lecture. I have a question. How is the CPA technique applied to the study of extra-dimensional physics? That's the question. Is that means that astronomy or something that's huge?
Well, I mean, it's, for instance, the things that we are trying to do now, trying to understand, maybe something which is close to what the student here wants, is something with the study of black holes, for instance, cosmology, okay, where we can produce very high, and this is related to what I said, we can produce very high accelerations, you know, and if you produce very large acceleration because of the equivalence principle, Einstein equivalence principle, which means that, for instance, accelerations, gravity accelerations, same and accelerations, then you can really produce, you could produce the equivalent of black holes, you know, very small black hole, for instance. And so you could really, you could study some of the maybe multidimensional effect, you know, and so on, yeah.
Mm-hmm. Yeah, very interesting. Next question, do we have enough time? So we still have a couple of minutes. So the next question is from, okay, the name Sakila. Good afternoon, sir. I would like to ask, since the ideal future of light research would to eventually be able to materialize light, what are the possible applications? This is an interesting question because you mentioned how lights can be materialized. So what are the possible applications in this case?
Well, I mean, the first application is try to understand light. Okay, and trying to understand light and trying to understand the vacuum, the quantum vacuum. And you know, I mean, you do that, how do you do that? It's like a high energy physicist, when you want to try to understand something, you break it, right? What high energy physicists are doing, okay? And when we will will be in what we call the Schwinger regime, but we will have the intensity which is capable of really breaking down the vacuum, okay? The photons will become matter, will break into electrons and positrons. All this has never been done, you know, with light, okay? And we may certainly we may find some very exciting discovery or application. Yeah.
So there are lots of rooms of applications for maybe inventions in this area actually.
Oh, absolutely. And I'm coming back again to the fact that now, and that's the reason why we are pushing to get shorter and shorter pulses. Because if we get shorter and shorter pulses, then it's very easy to get higher and higher peak power. But at the same time, you shift from the visible regime to the X-ray, gamma ray regime. So you have burst of light now, of X-ray light or gamma ray light, very intense. And this also, but there's a lot, my colleagues, you know, doing cosmology and so on, you know, would be crazy about this, you know. Okay. So that's a very important future,
yeah.
I tell you.
Sure, definitely.
The idea is really to do cosmology, you know, and in the laboratory, you know.
Oh,
yeah.
Okay. Yeah, yeah. I think it is very interesting for many of physics students. I mean, with this implementation with lasers, especially as a very short wave laser, it is of course very important for new discoveries. And one question which is coming from interesting question. May I see the name first? Okay. His name is Theodorus Panjaitan. Theodorus, thank you. This is more on your motivation, so how you can motivate them too. The question is, what was the drive of your discovery? Was it curiosity or the feeling of wanting to have humankind, or both, or anything else that you can
Well,
say?
I mean, first it's curiosity, okay? You know, it's just, I cannot resist, you know, trying to understand things, okay? Of course, you know, when you start, you know, you are students, you know, and so on, so you ask yourself a lot of questions. But then, you know, of course, all the questions you are asking yourself is very difficult for you to give an answer. But then, when you start now to go into graduate schools and so on and do research, then you have the means to ask yourself very hard questions and try to find the answer to these questions. So you know, I know it was first a curiosity for myself. And then, of course, then you find the applications. And sometimes, you know, you have serendipity working for you, okay? Like, for instance, when we discover the application in ophthalmology, it was really pure accident, I have to say. Accident, you know, in a proper sense, so in figurative sense, okay? It was a pure accident. One of my students was tweaking the laser, okay? And as he was tweaking the laser, he got the laser in his eye. Okay, and at that time, the femtosecond laser was a very new kind of lasers. So we took the students to the hospital, and he was examined by the ophthalmologist, and the ophthalmologist was amazed. And he said, my student was lying, you know, on the chair as he was examined, and the surgeon, in fact, he was an intern student, intern in medicine, right? And he said, I'm amazed. And the student said, what are you amazed by? He said, because you got this laser in your eyes, in your retina, but the damage is perfect. Oh. Because it was very clean, you know. So, you know, normally lasers were used in ophthalmology, but they were long pulse lasers, nanosecond pulses. So they make craters, you know, not this perfect, you know, removal of materials, you know, very, you don't hit the surroundings, you just hit only the very minute amount of matter that you care of. And that, it was immediately at the University of Michigan, they had the idea, they pushed us really to go into these directions. And so it was a serendipity, it was an accident. You know, I was a physicist, I was not really doing medicine at all. And I became very involved after ophthalmology, you know, with ophthalmology, of course. But these kind of things that happen to you sometimes.
Yeah, interesting. Yeah. Interesting story, Prof. MOUROU. I mean, like, this is what we call it. Maybe it's an incident, maybe it is just a coincidence, but it has
we call that serendipity. You know?
Yeah. Serenity, yes. Yeah.
Serendipity.
Yeah. Wow. Very interesting story.
But you know, a lot of discovery were made this way, right?
Mm-hmm. Yeah. Yeah.
Well, it doesn't mean that you have to do stupid things to get...
Definitely. And in this case, an accident that introduces new applications.
Yeah, because I was at... when this accident came at the University of Michigan, of course, you know, it was not taken lightly. It was not taken lightly. Yeah. It was... you had a commission to examine what happened and so on. And as we were discussing with the committee, which were investigating the case of this accident, then the president of the university realized that he was an engineer, you know, physicist, engineer. He realized how important it could be. You know, he understood that it could have big application for the eye surgery. Mm-hmm. So he said, okay, we are not going to close your lab, but we are going to give you more money so you can study this effect.
Yeah. Wow. Now the time is about, in Indonesia is 4:40. We have been, I think you have been talking for how long? Almost 1.5, maybe almost 2 hours. Mm-hmm. It's very, very interesting. I think lots of students are inspired. Many questions that I see here, and also in the audience in the Zoom meeting are also very, very appreciative. I can't actually read out all the questions, but probably you could also look at all these chats that are getting into the Zoom session. It was very amazing presentation, Prof. MOUROU. Mm-hmm. I think the most important thing now is that the students, I think, have very great impression about what have to be done for humankind. So mm-hmm. To solve the problems in the world, I mean, like, it is not something that is a utopia for us that has the ability to get into an academic atmosphere, to be able to do research, to join all these scientific activities. Any one of us can contribute and can do something to solve the problems. And you are one of the role models. I think with your presence here in Universitas Indonesia, I'm sure for this year's students, most of all the students here are well inspired, I can presume that. And of course, with this condition, the pandemic condition, where many of us are staying at home, we are, of course, keen to study, to maybe go to university. Maybe we have to do online. I know that last year, all the students are starting from home. None of them are going to university. Many of them do not know what campus life is yet. It's like home. It's like the same as what's staying at home. But I think the world also is going to change. The important thing is that to be inspired and to know that we can do what we can do. And in this world, I think one of the contributors, one of the very significant contributor to our global society is you. So you have been inspiring all the students, Professor MOUROU, and I'm thankful for that, for willingness to give a lecture today. And I wish you all the best.
Okay, well, I mean, thank you very much. It was a pleasure to speak at your really beautiful university. And I hope, you know, we will we will meet again, okay?
Sure, sure. I hope that you can visit us too. I mean, like, some of us can visit you. I mean, like, maybe one of a couple of students would have the chance to meet you later in the future. Yeah. And of course, before this, Professor MOUROU, we also managed to gather about 400 scientists and researchers in Indonesia and some from also globally around the world to discuss about the laser applications. And I think some of the audience in the Zoom meeting, they are also attending the event or the seminar to discuss about laser. And I hope this would also be a good chance to, let's say, to set up a good community or society, scientific society in Indonesia that can also later be collaborating with you and the team all over the world. So they are here, they are in the meeting room. So I think they all have greeted you also through chat. So I think just to inform you that Indonesia, we do have scientists or also researchers in the area, and we hope that in the future they can have some collaborations also. Yes, 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 yes. Okay. Okay, thank you very much.
Thank you very much.
Last statement or some closing statement, Prof. MOUROU?
For me?
Yeah.
Do you have closing statement? Well,
Yes.
As I said, you know, I think I'm really always glad to go to a new university that I was not. Of course, I didn't know about. I mean, I knew about the university, but I didn't know well. But now I know much better, and I would like to know much more now, because I think the reception was very good, and I was really pleased to speak to this. And I saw the first I mean, all the presentations, you know, I would say the commercial kind of things, you know, what you have before shows that, you know, this university is really prestigious. You know, I hope that I will have the time, really, to have the opportunity and the time, okay, to go and trying to visit it, you know, in more, you know, in more, you know, deep manner.
Yeah.
Yeah. So I would like to thank you, all of you, and thank the students. And I would like to say that you need to believe in science. I mean, we can see that now with coronavirus and so on, but there is people who are really still really wondering what science is, and it's not being interpreted in the right manner. And it's very sad sometimes to see that, okay? Well, we have a lot of way to inform people, but also I think a lot of times it's being used to misinform the people. And that is very sad. So I think it's very important for the students really to be very active also to informing people and trying to explain what science is around them, and because a lot of time it's really misinterpreted. And we see that in the States, we see that in France, we see that, you know, everywhere. And I think science has a lot to offer for scientists.
Yes, science has a lot to offer.
So thank you very much.
Thank you, Professor MOUROU. All the audience here are clapping for you. On behalf of Universitas Indonesia, I send my highest gratitude to you, Professor MOUROU, for your very generous lecture, very impressive, very motivating, very inspiring to us all in Indonesia. And we wish you all the best, good health, and of course, lots of success in your future endeavor to come. Thank you very much, Prof. MOUROU.
Thank you. Thank you. Au revoir.
Bye. Okay. Okay.
Baik, kami ucapkan terima kasih kepada Bapak Asta Ekadianto, Director for Center for Independent Learning Universitas Indonesia, yang telah memandu masterclass dengan Profesor Gerard MOUROU, pemenang Nobel Laureate Fisika.
Luar biasa tadi kalau kita mendengarkan penjelasan dari Prof. Gerard terkait dengan inovasi, kemudian juga penelitian secara global, dan ini mudah-mudahan bisa menumbuhkan semangat para mahasiswa baru untuk menjadi peneliti-peneliti berikutnya.
Betul
ya,
sekali,
Sasti, ya?
Semangatnya sangat terlihat lah di Mas
Iya.
Saska ya.
Bahkan
Banyak
pertanyaan-pertanyaan
sekali
yang masuk juga sangat bagus sekali ya,
Betul,
Sasti, ya. Bahkan
betul.
tadi ada dari Fakultas Fisika dan sebagainya itu sendiri ya.
Betul sekali, dan Reska, setelah ini kita akan kembali mengajak teman-teman mahasiswa untuk mengisi assessment virtual formulir seperti kemarin, dan kami ingin menginformasikan juga untuk talk show yang tadi sempat tertunda akan kami lanjutkan di besok hari.
Jadi tidak perlu khawatir gitu ya.
Iya.
Masih ada waktu esok akan menghadirkan dengan narasumber-narasumber menarik lainnya ya.
Betul sekali.
Baik, ini saatnya kita mengajak kepada seluruh mahasiswa baru Universitas Indonesia untuk mengikuti assessment test ya.
Iya,
Dan
betul.
seperti biasa, seperti kemarin harus segera mengisi link yang sudah tertera di layar Anda atau yang sudah ada pada Anda sendiri. Jadi silakan saja Anda untuk mengisi segera karena ini merupakan syarat untuk mendapatkan jaket kuning. Dan waktu pengisian selama 30 menit dimulai dari sekarang.
Bermimpi memiliki uang 1 miliar di masa pensiunmu, sekaligus memberikan sumbangsi untuk alma mater. Yuk, mulai berinvestasi di reksadana aja. Produk reksadana yang cocok untuk kamu adalah reksadana BNI AM Makara Investasi. BNI AM Makara Investasi adalah produk investasi berbasis reksadana pendapatan tetap yang diterbitkan oleh BNI Asset